Another law is the Avogadro's law, and this one states that equal volumes of gases measured at the same temperature and pressure, they do contain same number of molecules. This is why we're relating it to Avogadro's law, because the number of molecules is also related to Avogadro's number, right? So when we say standard conditions, this means STP. STP means the standard temperature and pressure. The standard temperature is well known to be 0 degrees Celsius, so it's 273 Kelvin. And the standard pressure is 1 atmosphere. So when you are working with a problem that starts with at STP, it means the standard temperature and pressure. They won't give you the temperature, they won't give you the pressure, so you have to assume that the temperature is 0, and that corresponds to 273 Kelvin, and the standard pressure is equal to 1 atmosphere. So at STP, the volume of 1 mole of gas, so that's why we call it the molar volume. So the molar volume is the volume of 1 mole of gas that is measured at the same temperature and pressure, okay? That is going to correspond to 22.4 liters, and it should contain the same molecule. So if I'm looking at all of these different gases in there, all of these different gases at the same temperature and the pressure standard, not the same, it's standard temperature and the pressure. So at temperature 0 degrees Celsius, pressure 1 atmosphere, all of these gases, they have a molar volume, which is a volume of 1 mole, corresponds to 22.4 liters in there, and they contain the same number of molecules. Another gas law is the ideal gas law, and this ideal gas law, it allows the calculation to be done in which you can vary the amount of the gas, which is the number of moles. This is the N over here. As well as you can vary the temperature, you can vary the pressure, and you can vary the volume. And this formula that you see over here is the formula for the ideal gas law, where you can vary the number of moles, the pressure, the volume, and the temperature. R is the gas constant, and R has, it's a constant, right? Because it's a constant, it does have a constant volume. And notice the units for the R, it's very important. So this will tell you what are the units of the pressure, the volume, and the temperature. What should they be so that they match the R units? So the volume has to be in liters, the pressure has to be in atmosphere, and the temperature has to be in Kelvin. So please pay attention to that. Let's go ahead and have an example. A 2.50 moles sample of gas is confined in a 6.17 liters. So I'm given the number of moles, which is N. So N over here is the number of moles. I am given the volume, and I'm given the temperature that I need to change into Kelvin, and then they are asking me about the pressure. So in this case, I know that I would need the ideal gas. So let's write it down. PV is equal to nRT. So we need the pressure, right? So the pressure is equal to nRT divided by V, because I'm just going to go ahead and divide by V here, divide by V there, so that I can cancel the V out. And then go ahead and do your substitution. So 2.50 moles multiplied by the R. And I always insist on you writing the units for every single variable. Reason why? Because we want to make sure that the units, they do match. So when we say mole to the -1, K to the -1, this is actually in the denominator. It should be in the denominator. It means dividing. So you're dividing by mole, Kelvin, like that. And we're going to multiply this by 301 K. We change the Celsius into K. And here you go. And we are going to divide this by volume, which is 6.17 liters. So that is going to correspond to 10.0 atmosphere. Let's have another example. a 4.00 grams of sample of gas is found to exert a pressure of that much when confined in a 3.6 liter container. So you're putting that gas sample in a container at this temperature. What is the molecular weight of the gas in grams? Guys, we already know the relationship between, this is the relationship that we started with between the mass and the moles, because we know to go from the mass to the moles, we're going to use the molecular weight, right? And this is the equation over here. The molecular weight is the mass divided by the number of moles in there. You can put it in a form of a conversion, or like this, or you can put it like this. I mean, both are the same in there. So molecular weight is the mass divided by the number of moles. And the question is to find this guy, okay, to find the molecular weight. So to find the molecular weight, I would write the equation for the molecular weight, which is this. I already am given the mass, right? I'm already given the mass, and the mass over here is 4.00 grams. So I already have this guy. I'm good. So now to get the molecular weight, I need the number of moles. From where you're going to get the number of moles? From the ideal gas law equation, which is the PV equal nRT. So you have all of those over here. We're going to go ahead and do the substitution. So that is 1.71 atmosphere multiplied by 3.60 atmosphere divided by 0.0821. This is liter atmosphere. Again, by writing the units, you will always remember to convert the units if you did not, because here atmosphere and atmosphere, they you can take those out. You do have 300 Kelvin. This one is not atmosphere, my bad. This is liters in there. So let's go ahead and put it as liters in here. So atmosphere and atmosphere will cancel. Liters and liters will cancel. Kelvin and Kelvin will cancel. So I'm going to be only left with the moles, which is going to be my unit in this case. So here I'm going to be 0.250 moles. Okay. Now, once I get the moles, I can go ahead and substitute it in this equation. And I would say that the mass is 4 grams and the moles is 0.250 moles. So the molecular weight unit is grams per mole, always. Another gas law is the Dalton's law, and Dalton's law deals with mixture of gases. So let's say, for example, if we have a container of oxygen gas, it will read a certain pressure. And then if we have another one with like nitrogen gas, it will read also another pressure. And if we have hydrogen, it will read another pressure. Now we take all of these gases and we put them in one container. The sum of the pressure is going to be equal to P1 plus P2 plus P3. So the final pressure here is going to be the sum of all the individual pressures. This is what Dalton's law is. It's P total is equal to P1 plus P2 plus P3. It's the sum of the pressure of each individual gas in the container. So let's go ahead and have an example here. It's going to be for different gases. So a container contains helium. It has a pressure. Neon has a pressure. Argon has a pressure. So if I ask you what's the total pressure in there, you would say, okay, the total pressure in the container is equal to the pressure of the individual helium gas plus the pressure of the neon plus the pressure of the argon, and that is equal to 0.5 atmosphere plus 0.6 atmosphere plus 1.3 atmosphere, and that is equal to 2.40 atmosphere. Okay. Graham's law, this is an expression that relates the rate of effusion or diffusion of two gases to the masses of the molecules of the two gases. So by definition, we do have two processes here by which the gas goes from one medium to the other. So effusion, what is that? It is the process in which the gas escapes through a small hole in a container. If you have a container, you have a small hole in there. The gas is going to escape slowly. This is called effusion. Diffusion, it's the process that causes the gas to spontaneously mix when they are brought together. So let's say, for example, if you have a column, and at the end of the column you have HCl. This is hydrochloric acid that that actually results in an HCl gas. And then you have ammonia on the other end of the column. Also ammonia results in an ammonium fume or gas. So ammonia fume or gas will simply diffuse. This means that it's going to travel through the tube, and the HCl gas is going to travel through the tube, and they're going to meet at a certain point. Once they meet, they're going to do a chemical reaction, and here this is a combination reaction where ammonia will react with HCl gas, and you're going to get a white precipitate, a white solid in there that you're going to see. It's going to be a white line on that tube, which is ammonium chloride. That process is called diffusion. It's when those two gases, they spontaneously they travel and they mix together when they are brought together. Graham's law has this relationship. So the effusion rate of gas A, effusion rate of gas B is equal to the radical of the molecular mass, which is the molecular weight of gas B divided by the molecular weight of gas A. So let's have an example here. It says calculate or compare the rates of effusion or diffusion for neon and krypton gases. So since I need the molecular weights in there, I'm gonna go to the periodic table and check the molecular weights of krypton and neon. So the molecular weight of krypton is this, 0.80. And this is atomic mass units. You can go ahead and say that as grams per mole. It's not a big deal, but I'm just going to keep it as atomic mass unit. And the molecular weight of neon, that is 20.18 atomic mass unit. So I would say that the rate of neon divided by the rate of krypton, that is equal to its inverse, okay, to the inverse of the molecular weight. So since I started with neon in here, I have to start with the molecular weight of the krypton. So that is going to be 83.80 units divided by 20.18 units, and that is equal to radical 4.153. Use your calculators definitely for this one and for every single problem that you do. So I would say that the rate of neon is equal to cross multiply. Okay, this is over 1. So what you can do is simple cross multiply in here. So this is the rate of krypton times, so rate of neon is equal to the rate of krypton times 2.038. Okay, so it's equal 2 times the rate of krypton, right? This is what it means. Rate of neon is 2 times the rate of krypton in there. So I would say that neon, therefore, neon gas effuses, of course, is going to effuse about twice as fast as the krypton. Effuses or diffuses, okay, about twice as fast as krypton gas. Okay. And then we have another form of problem where you might need to calculate probably the you're given the density and you would need to calculate the molar mass. Okay, something like this. Always remember that density is equal to the mass divided by the volume. Okay. And always the volume depends, of course, on the pressure and on the temperature. Density changes for solutions with different pressures and different temperatures. So pay attention to this. Okay, so if the density of neon at STP, so I'm given STPs, remember, standard temperature and pressure means that I have 1 atmosphere pressure and the temperature is 0 degrees Celsius. So I'm given the density of neon to be that much, 0.900 grams per liter. What is the molar mass of neon? Okay, the molar mass, the first thing I would do is determine my units in there. What's the unit for the molar mass? So what I need at the end is to find the molar mass, which is simply grams per mole, right? This is what I need. So I am given grams per liter, and I want to change this into grams per mole. And I am given that the density of neon is at STP. So at the same time, when they give me STP conditions, I know that at STP, at standard temperature and the pressure, so I would say that at STP, 1 mole of gas contains 22.4 liters. And this is a fact. This is a well-known fact in there that at standard temperature and pressure, 1 mole of gas corresponds to 22.4 liters of volume in there. And the reason why I need this information, because I can use this to cancel the liters and introduce the moles. So let's put our equation now. So I'm starting, always start with your given, you guys. So I'm starting with the density, which is 0.900. That is the grams per 1 liter. I want to cancel the liter out, so I know that 22.4 liters or 1 mole of gas occupies 22.4 liters. So 1 mole of neon gas occupies 22.4 liters, occupies a volume of 22.4 liters at standard temperature and the pressure. That's it. I can cancel my liters in there, and my answer is going to be in grams per mole. Okay, let's have another example. The molar mass of sulfur dioxide, this is, by the way, the hardest it can get in there whenever you are asked to determine the density. You have the molar mass. So the molar mass of sulfur dioxide is 64.07 grams per mole. We're going to go ahead and determine the density of the SO2 at standard temperature and the pressure. So we're going to do the same thing in there. And we're going to say that at standard temperature and the pressure, so at STP, 1 mole of SO2 gas occupies 22.4 liter volume. So I'm starting with 64.07 grams per mole, right? I need the density. Now, what is the density? The density is the grams per, you can say grams per liter in this case. This is what the density is. So the units for the density are grams per, it's the mass divided by the volume. So these are the units that I want to reach. So I want to get rid of the moles now. So I know that 1 mole corresponds to 22.4 liters. So I can cancel the mole and the mole out, left with the grams per liters in there, and this is going to be your answer. Okay. More ideal gas problems. These are similar to the ones in your homework, you guys. So what is the volume of 2.00 moles of krypton gas at standard temperature and pressure? So I can give you something like this, do not give you any temperature or pressure there, and say just STP. So you have to directly deduce that the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. You already know what the R is. This is a constant, you guys. Write it down. And what is the volume of 2 moles in there? It's not the 3 moles actually, it is 2 moles. So we're going to go ahead and put 2 moles over here. You can do the conversion. V is equal to nRT divided by P, and then do the substitution in there. So it's going to be 2 moles times 0.082 liter atmosphere mole Kelvin, and then we're going to multiply this. Remember guys, temperature has to be in Kelvin every single time, and the pressure here is 1 atmosphere. This is the standard temperature and the pressure, and your volume is 772, and it's in liters, okay, not in mils, it's in liters. Another problem, this is similar to the molar mass problem that we did earlier. So they need the molecular weight. So if they need the molecular weight, we already have a formula between the molecular weight and the mass and the number of moles, okay, which is M. So we can, so this is mass divided by N in there. So we can simply calculate N from PV equal nRT. So N is equal to RT divided by PV. We can get N, okay? And remember that T is 0 degrees Celsius, so it's 273 Kelvin, and the pressure is 1 atmosphere. So once we get N, we can simply put it in the equation here, and we know the mass is 16, we can get the molecular weight. Guys, this is one way. Another way is simply to make a new formula by substituting the N, because we know that the number of moles is equal to the mass divided by the molecular weight. So we can do this. So we know that the number of moles is equal to the mass. You can shuffle that equation around, divided by the molecular weight, right? So we can come over here and say, okay, so we can substitute the N here by the mass divided by the molecular weight, so that we can come up with a new equation, and you can put this in your cheat sheet. I think I added it to the list of the equations of the gas law in the cheat sheet there, where you can skip the number of moles and have a relationship just between the molecular weight, the mass, pressure, volume, and temperature. Okay, so if I do the rearrangement here in this case, implies I can simply get the molecular weight to be equal to the mass multiplied by R. This is my new equation, divided by P times V. All I did is I simply cross multiplied, and then I divided by PV so that I can get the molecular weight equation. So this is the molecular weight equation. As I said, please add it to the list of your formulas. And with this equation, we bypass the number of moles. We don't need to calculate it and then put it again. We directly have everything. We have the mass, we have the gas constant, we have the T, we have the P, we have the V. P, as I said, is 1 atmosphere, and the temperature is 273 Kelvin. So if you plug everything, your answer is going to be 29.9 grams per mole. Okay, another example. What volume of carbon dioxide gas is produced when 3 moles of oxygen gas react completely in the following equation? So if you look at the equation, we can simply relate the number of moles of oxygen to the number of moles of carbon dioxide, right? So we would say that for every 1 mole of oxygen, so for every 1 mole of oxygen that you react, you produce 2 moles of carbon dioxide, right? So we can calculate, since they need the volume of carbon dioxide. So if they need the volume of carbon dioxide in there, I cannot calculate the volume of oxygen. Because if I use PV equal nRT, the number of moles given is the number of oxygen. moles, not the carbon dioxide. So I have to find out the number of moles of carbon dioxide from the oxygen and then use PV and RT to calculate the volume of the carbon dioxide. So first we're going to calculate the number of moles of carbon dioxide. We are given 3 moles, 3.00 moles of oxygen. So I'm going to relate this to the moles of carbon dioxide. I want to find the moles of carbon dioxide, so I would do this relationship. I'm forming 2 moles of carbon dioxide for every 1 mole of oxygen. So 2 moles of CO2 for every 1 mole of oxygen. So the moles of oxygen cancel out, and that is going to be 6.0 moles of CO2. This is the number of moles of carbon dioxide. So this is equal to N of CO2 there. Okay, so now I know that PV is equal to nRT of the CO2. I need the volume of the CO2. So that is equal to nRT divided by P. Everything is going to be for CO2. Okay, not for oxygen. So that one is going to be for CO2. So the N for the CO2, I got it, which is 6.0 moles of carbon dioxide. I'm going to multiply this by the gas constant. This is liter, atmosphere, mole, Kelvin, okay? And then by 273, which is the temperature, which is, they said over here, since they didn't mention anything about the temperature, so probably this one is an at STP, standard temperature and the pressure. So the, let's add it. So here, at STP. Okay, and the pressure is going to be 1 atmosphere. So the answer here is going to be 134 liters. Okay, practice the problems. You do have the answers for the problems, the detailed solution for the answers of the problems. Please look at it, practice your homework, and make sure that you submit your homework as well.